So today, what I'm going to do is talk about this assignment 1 right here. And this is due on Friday, midnight. And what assignment 1 is going to look like is it's a set of questions. What it does look like. It's just a set of questions. And I ask you to analyze the code and answer some question about the code based on your analysis of the code. You don't have to write out your analysis. You don't have to give your reasoning. But you need to use your reasoning to come up with this solution. And this is meant to be done without the aid of the computer. So this is kind of like practice for the quiz. And this assignment will look very much like the quiz. And of course, the goal here is for you to learn how to reason about algorithms, very simple algorithms. You know, add 1 to x, and do something else, and continue that process while x is less than 100. And does that algorithm, the way it's described, solve the problem that we're working on? So that's the value of this exercise, right? It's to start to think computationally. It's to start to exercise your creative abilities to solve problems that have a computational or algorithmic solution. So this is what you need to do. And you can, what you need to do is submit your answers through the repository, just like you're submitting your lab assignments. So what you can do there is, let me see. I've created a folder called A1. This is what you should do as well. Create a folder called A1. And inside that folder, create a file and put your answers into that file. And then when you're done, commit your responses into the repository. All right, so what I did was I just copied over some of the problems that are from the assignment. I'm not going to go over the exact same problems because that wouldn't make any sense. You need to figure out the solution to these problems on your own. So let's take a look at what I've come up here for question 1. All right. Question 1. So here I give a figure, figure 1, and it's some lines of code. It's not a complete program. There's no main function and things like that. So it's a code snippet of code, piece of code. And now your job is to understand what this code does, and then based on that understanding, answer this question. So when the code in figure 1 runs, what does it output to the console? Well, let's try to understand that. Look at the first line. We create a variable x and initialize it to 0. So we have 4 bytes of memory allocated, and it's labeled with the variable name x, and the number 0 is placed in there. It's represented in there. So it's 32 bits all set to 0. That's what a 0 is in memory, for an int. And then we come into this loop. It's called a while loop. There's 2 kinds of loops that we're going to look at, while loops and for loops. There's other type of loops as well, but these are the common ones, most common. And so what this while loop does is it repeats the execution of a block of statements, 0 or more statements. Here we have 1 statement in the block. The block is delimited by an opening brace and a closing brace. You could have any number of statements in there, including no statement at all. The braces are optional, so if we took them out, what the compiler does is it says, oh, there's no braces there. That means you only want to repeat a single statement. So it looks at the next statement. It doesn't care about the indentation. It just looks at the next statement. And then it repeats that statement as long as the loop condition evaluates to true. The loop condition is the condition, the expression, that's in the parentheses. I'm going to put the braces back in there because I think it's easier to see the logic, and it's also, when you're actually doing programming that's intended to run on a computer, that this can help to avoid a certain kind of bug where the programmer doesn't realize that the loop is only executing one statement. It may appear as if there's several statements that are indented. It gives the appearance that a block of statements are being run, but really one is being run. You can avoid that potential bug by always using braces, even when you have a single statement in your block. All right, so k is initialized to 0, and then we come into this loop. So the loop is going to repeat, it's going to execute repeatedly its block of statements as long as the loop condition is true. So the loop condition is that k is greater than or equal to 77. Well, because k is 0 when we first reach this loop, that the loop condition is in fact false. And I was going to make it true, but that's going to be false. And so 0 is not bigger than or equal to 77. So we never execute the block of statements. And then we're going to print 2 times I. Now, I is undefined. So this problem, I was just doing this now before I started the lecture. I really wanted to do that. Okay, so 2 times k is 0, so we would output 0. So your answer here would be 0. All right, let's change the problem a little bit. Let's do the other direction. Suppose that were to be the loop condition. Now, when the loop condition is first executed, it's evaluated to true, because 0 is less than or equal to 77. So now we're going to execute this block of statements, a single statement, and we'll take what's in k, which is 0, add the 5, and that gives us a result. It gives us, we say that the statement evaluates to 5 in this case. And that number is just, it's actually sitting in a register in the CPU. And what we want to do is take that number, which is sitting in the register, in its high-speed registers in the CPU, and we write it out into RAM and store it in those 4 bytes that are being used to store k. So we place 5, k was 0, and now we're writing a 5 into that storage location represented by k. So k becomes 5. And there's a single statement to repeat. So now we need to, after we execute those statements, we need to check the loop condition. Now we compare k to 77 again, but k is now 5, so the loop condition is still true. And so eventually k is growing here. So eventually k will exceed 77, and then we will print 2 times whatever k is. So what's the answer here? Anybody know the answer? I don't have very good hearing. 160. 160. That looks good to me. So everyone, you need to reason about that, right? I'll try to reason out loud so that for those who didn't get the answer, maybe you can understand it. The k starts at 0, k becomes 5, then it becomes 10, then it becomes 15. So it's increasing by 5, so it's going to hit every multiple of 5. And it'll hit 75. When it hits 75, the loop condition is true. And then it'll add 5 to k, and then k will be 80. And when k hits 80, the loop condition is false. And that means we stop executing the loop, the statements in the loop. Now k is 80. So we're going to multiply 80 by 2 to get 160, and then we print it out. Well, the answer would be 160. What about this? What do we get now? Can you reason about this code? And in fact, how about if we do this? It's hard to figure it out, right? A little tough. 1,000. 1,556? Okay. Anybody have a different answer? I didn't figure it out yet. It's but I'll show you how I would think about it. I kind of would need to use some scratch paper. Let's see if your answer is right. That's good that you were able to come up with something. That's great. So look at k. K is going to start at 3, and then it's going to go to 8. Then it's going to go to 13, and so on. So it's going to increase by 5 each time. So it's going to be 3 plus some n times 5. Now the problem is, in this sequence, when does it hit, pass or hit exactly 777? Well, let's take, let's see, if we divide, let's see, what's a good value for n here? Anybody got a good guess there? So 1,000 is going to be too big, right? Oh, but this is just n. I see. So the answer, once we figure out, well, let's see, let's get a number that's near, let's find an n that's near 777. So it's 777 divided by 5. 2, 5, you getting there? That would be, let's see, that's, could someone do 777 divided by 5 for me? It's not 2, actually, it's 1. 27 is left over, that's another 5, right? Something like that, 27, huh?
155.
155, okay, good. So when we have, let's take n to be 155. So 155 times 5 is going to give us, let's see, 500 plus 250 plus 25. What do we get for that? So it's 7, 7, 5. I get that? All right, so when n is 155, then this expression here, n times 5 will be at 775. So it'll be, so k, this is, by the way, these are the values, let me just make this more clear. These are the values that k takes on. These are the values that k hits. What's that? Oh, so it's not 3 times. Yeah, that's right. That's 3 plus. Thank you. So when n is 155, this expression, n times 5, is 755. And if we add 3 to that, we get 778. Is that right? So that's actually, we're 1 past, that's the value that k takes on. So we're 1 past 777. So k will hit 778 at some point, and that makes the loop condition false. And then we multiply k by 2 and print that result. All right, what's 2 times 778? 1556? That's it. You got it. Good. Good job. A lot faster than me. All right. That reasoning process, you need to do that on the quiz and on the assignment as well. This particular problem, I asked this kind of problem in both the assignment and the quiz. I would say this maybe is the hardest one that you need to do. This is the hardest problem that you'll need to do on this assignment. All right, let's take a look at this one here. Now here's a for loop. And it executes a single statement. And the problem here is not to figure out what it displays, but simply to rewrite it so that the code uses a while loop rather than a for loop to accomplish the same output. All right. So we want to use a while loop. Let's start by just seeing what that's going to look like. There's going to be while, there's going to be a loop condition in here, and then there's going to be the statements in here. And this is the initialization. So it's pretty straightforward actually to do this. This is when the for loop runs, you have 3 sections in here. The first section is initialization. That's when execution reaches the for loop, the initialization section runs. It runs once. After the initialization section runs, the loop condition is evaluated. If the loop condition is true, the body of the loop runs. After the body of the loop runs, the end of loop operation runs, increment I. And then we continue. Well, we don't continue with initialization. We continue by evaluating the loop condition, running the body of statements, do the end of loop operation. We can do that over and over again until the loop condition is false, and then we're done. So initialization is pretty straightforward here. So we need to declare an I and set it to 0. The loop condition is also similarly straightforward to extract from the for loop. I less than 10. That's the loop condition. That's the thing that, when true, makes the body execute. And the statements to repeat, that's a little bit, takes a little bit of thinking to get that right. We're going to do this. That's the thing that repeats. But there's something else that repeats. There's that end of loop operation, this incrementing of I. This is the end of loop operation, so that has to be done at the bottom of the loop. So that would be the very last line. This means increment I by 1. These two loops are equivalent. Maybe on the assignment or the quiz, I give you a while loop and ask you to express that as a for loop. I could do that. So there's essentially, all loops can be written in all the other forms. Any questions on this? Okay. Let's take a look at this one. So the question is, how many times does the body of the for loop run in the code of figure 3? Here's the for loop. There's some declaration, initialization of k going on here. K is set to 4001. K appears in the loop condition, but the loop has its counter is not k, the counter is I. That's the thing that gets incremented here. And this is the statement. You'll see that I is involved in the statement that executes. But the key point to notice here is that I is used but not changed inside the body of the loop. So we take I, we add 1 to it. Now that result, let's suppose that I is 7, okay? And we add 1 to I, it becomes 8. What do we do with the 8? We don't store the 8. We get an 8, but the 8 is just sort of floating there. It didn't get written into I. We're not modifying I. So we calculate an 8. The 8 is just there. And what do we do with the 8? We send it into the standard output stream. We write it into the standard output stream. It gets displayed on the console if the console is connected to the standard output. But this does not modify I. It just uses I. So that's the key point that you need to grasp about this particular problem. Well, one of the key points. So actually we can ignore this statement. It has no influence on our answer to the problem. So K is set to 4001 here. And notice that after we set K, we don't touch it again. We just read it. We look at it. We use it as part of the loop condition, but we never modify K. So this code would be equivalent to doing this. This would be this, give us exactly the same result. So how many times does the loop condition run? I mean, how many times does the body of the loop run? Is it 4,000? Is it 4001? Is it 4002? Somewhere in there. There's this problem in computer science. It's called what do they call it? I can't remember now. Off by 1 problem. I think that's what it's called. Off by 1. And it's very easy to be off by 1. So you can, it's like playing golf. You know, you've got your driving iron. You hit the ball near the hole, it gets in the green, and then you have to take out the putter for the precision hit to get the ball in the hole. Just like that, we know that we're going to be somewhere around 4,000, but now we need to use some reasoning and sharpen up our understanding of the problem and get a precise answer. So we start counting at 0. And then we compare 0 to 4001. We're going to run this once, right? And then Then I is incremented to 1. We're going to continue that until I hits 4,000. I will hit 4,000. And then we're going to do this. And then we're going to hit 4,001. And then the loop condition is false. So we do not execute the body of the loop when I hits 4,001. But we do execute the body of the loop when I hits 4,000. Now, if you started at 1 and went to 4,000, you would have 4,000 times. But we started counting at 0. So we're going to execute the body of the loop 4,001 times. We start at 0. We hit 4,000. We run the loop at 4,000. That's 4,001 times. 4,001 executions of the body of the loop. And then we go to 4,001 and we're finished. We don't go into the loop body anymore. Any questions? What's that? 0 what? 0 is counted. Well, yeah, I guess you can say that. 0 is counted. We could say it like that. It's not exact. There's other ways to think about it. You could think of it as 0 is being counted. You could think of it like that. But it's you might want to think a little bit differently. You've got a variable I. It's set to 0. That's its state, its value. And how many times does the loop condition evaluate to true? Well, I state starts at 0, then it goes to 1, then it goes to 2, like that. And for each state that I takes on, which is less than 4,001, the loop runs. So in that sense, you could say that 0 is counted. Okay. Any other questions? What I'm trying to do is sort of think out loud in a computational way so that you can sort of pick that up. I wouldn't say 0 is counted. Yeah, I like your question, by the way. I don't mean to hammer on you and criticize you or anything. But see, I'm trying to kind of use the right terminology, the right word, and convey the concepts that you need to have in order to think computationally. All right, let's take a look at this one. When the code in Figure 5 runs, what does it output to the console? Well, that looks like a mess, right? Does that give you a headache when you look at that? Okay. Well, what you can do is just sort of calm down and say, all right, I'm going to parse the expression. I'm going to start at the left. I'm going to read each character one at a time. I'll think like the computer does. The computer's not emotional. The computer I'm going to start at the C, and then there's an O, then there's a U, and I got an operator here. And then I've got an expression. So the operator takes something on the left-hand side and something on the right-hand side. And then I've got another operator. Oh, I got to do two things, but we're not going to do two things at once. We're only going to do one thing, and then we're going to do the next thing. So which operator runs first? It's different for each operator, but if you don't remember the differences, then just say left to right, okay? Because they're almost all left to right. So left to right evaluation means this. It means that operator, because they're the same operator, this operator runs first. And the result of this operator running, it has two operands. It has an operand on the left, C out. It has an operand on the right, which is an expression that gets evaluated to a number. And then the operator gets the number on the right, and writes it into the standard output stream. But then it does one more thing. Well, sort of in a sense, the expression after it's kind of processed, the expression evaluates to the left-hand side of the operator, which is Cout. So this whole thing, after that expression, after what's inside these parentheses is run or processed, this is the result. What's inside the parentheses then becomes Cout. And then we have the same situation. We have the same operator appearing twice, so it's left to right evaluation. And so I'll put parentheses in there just to show you what runs next. And once again, that output operator, after it runs, it evaluates to the left-hand side, which is Cout. So finally, the third execution of that operator looks like this. All right, so let's go through this now. I'm just going to put it up like this. All right, so now to carry out the first task, which is to output this expression 1.0 divided by 4, I need to figure out, I can forget about the output operator. Put that aside. We're just going to take 1.0 and divide by 4. And what do we get? Well, we get 0.25. Now, this symbol is the same symbol as this, but they are two different operators. It's like, think about it like this. You call someone bad in one situation, and you call someone bad in another situation. Well, bad means good in that situation, but bad means really bad in the other situation. It's like, it's the same word, but it has two different interpretations based on its context. So in this context, the division symbol is used with a floating point number 1.0. And so the compiler interprets this as floating point division. But here, the symbol appears between two integer values. And so the compiler says, oh, you know, you're not really bad, you're just good. And so I'm going to interpret that as integer division. All right. So 1.0 divided by 4 is 0.25. That means we write 0.25 into the standard output stream. And after we write 0.25 into the standard output stream, this whole expression, in a sense, vanishes and is replaced by Cout. And that Cout is used as the left-hand argument to another output operation, which then gets a comma. So we're going to print a comma and a space. Did you notice I put a space in there? So it was easier to read the output. Then, after this output operation runs, and we have this situation down here, that this completes, and this is, so the expression in a sense vanishes and is replaced by Cout, and we get this expression. Okay, to carry out that expression, we need to take 1 divided by 4. Remember, that's integer division now. It's not floating point division. 1 divided by 4 in integer division is 0. Because we truncate. We don't do rounding. To round, you have to add 0.5, okay? So we take 1 divided by 4, and so we get a remainder. And all we have is a remainder. We have quotient of 0 and remainder of a remainder of 1. And so we toss the remainder out. We just take the quotient. So we're going to get a 0 there. And that's it. Any questions on this? So essentially, you're learning how to parse an expression, how to parse the same symbols that the computer parses. You're thinking like the computer. All right, let's look at this one. How does the computer parse this? Parsing means to understand it, to process it, to get ready to execute it. And of course, let's parse it so we understand it, and then let's sort of execute it in our mind. Let me read the question first. When the code in Figure 6 runs, what does it output to the console? All right, I'll start with the first statement. Int I. Okay, I'm declaring a variable I to be an integer. Equals 2. Oh, I'm assigning 2. By the way, this is not the equals operator. We don't say that's the equals operator. We don't say that. We say this is the assignment operator. This assigns the value 2 to the variable I. You know, it was unfortunate actually that that there was no better symbol for assignment. I've seen this before. This is an alternative way to represent assignment. Take 2 and write it into I. That's what it is. No, it's an action. It's an operation. It modifies the state of I, modifies the bits that are appear in the 4 bytes of memory that I is associated with. But that's assignment in this language, as it is in most languages, computer languages. I is set to 2, and K is also allocated and defined, and it's set to the result of this expression. So it's not as simple as this one. We need to evaluate the expression, come up with a result, and then store that into K. And then the third statement is we have this operator. This is one operator, by the way. Plus plus is a single operator. It's the increment I. Now this is a prefix increment. This is the postfix increment. And here's another operator, which is multiplication. Take the thing on the left with the thing on the right, multiply them together, and get a result. And this increment operator just operates on, it modifies the state of the variable that it's associated with. So here, this is modifying the state of I. It's adding the value 1 to I. Here it's also adding 1 to I, but there's a difference between these two expressions. And I'm going to get to that in a minute. And then there's another operator here, which is to do addition. So there are 4 operators in this statement. And you have to see which operator do I need to evaluate first. And you can use your common sense. There's something called operator precedence, which is which operator you're going to do first. It's like it's sort of common knowledge from math. If you did 6, times 2 plus 1, let me do it a little differently. Let's do it like this. I'll put the times here and the 1 here, just to make my point. If you look at that expression, do you get 18 or do you get 13? You get 13 because multiplication has a higher precedence than addition. So you do the multiplication first. If you wanted it the other way around, if you wanted 18, you would have to be explicit about it like this. You would have to override the default precedence of operators and say, hey, I want to do the addition first, then do the multiplication. All right. So here, is it possible to do this operator first? Well, what would we output? It's reasonable. You can see that this will have to run last. So this has a lower precedence than all the operators on the right. This increment operator has the highest precedence. We're going to do that first. And then multiplication has the next highest precedence, followed by addition. So first is increment, then multiplication, then addition, and then the output operator. So it doesn't look like left to right evaluation. See, left to right evaluation is only, that notion is only used when you have the same operator involved. So if I had, 1 plus 2 plus 3, the first plus runs, and then the second plus runs. That's a left to right evaluation. It's the same operator. All right, let's go through this now. Assign 2 to I. And then we increment I and multiply by 2. The only thing is, this is a prefix, a postfix increment. So the increment is done after I is used in the expression in which it appears. So the increment is done after the variable is used within the expression in which it appears. So we have to use I in the expression in which it appears, and then we'll increment I. So I is 2. Let's multiply 2 by 2. We get 4. And then we increment I, and then I becomes 3. And then we store 4, which was the value of the expression, into K. So the result here is that K gets 4 and I gets 3. What's that? Why does I get 3? Well, because we increment I here. I plus plus means I is initialized to 2, and we increment I here, so I becomes 3. But before we do the increment, we use I in this expression here, so we got to take the 2 times 2 to get 4, see? After we use the I, then we're going to increment the I. That's the key point here. That's a postfix evaluation. Post-evaluation. Delayed evaluation. This is the opposite. Here, the state of I is modified first, and then the expression in which it appears is evaluated. So, what does it output? Well, we're going to increment I here. I becomes 4. And then we use the result, 4 times 2, that's 8. And then we add it to I, which is 12. And we write 12 into the output stream. You want me to go through that again? Okay. Let's take a look at this. Well, that's the easy part, right? So we got to figure this out, and then whatever that is, we're going to print that. Okay. So let's just replace things in there. We're going to increment, I. It's not a precise to do it like this, but we're going to say, well, we're going to increment this value 3, multiply by 2, and then add 4. I mean, you could think of it like that, right? So the 3 becomes a 4. That's the first thing that happens. And then you've got multiplication and addition, so you've got to do the multiplication first. That becomes 8. And now we only have one operation remaining. That's the 12th. The increment is done first. The multiplication is done second. The addition is done last. And then, of course, we get a 12. Then we write 12 into the output stream. This expression where the pre-increment is much easier to think about, to reason about. It's the post-increment that's hard to reason about. So when you see the post-increment, you say, oh, trick question here. I'm going to have to think about this one. But when you see the pre-increment, you can say, well, yeah, I'm just going to add 1 to I right away. That's the first thing I do. Nothing else is going to go in front of me. That's the operation I do first. That's his highest priority. So that's very easy to understand a pre-increment. But the post-increment is a little more work mentally. Because you got to say, oh, I got to increment I, but no, before I do that, I got to use the I within the expression in which it appears first. After I use the I, then I'm going to increment the I. All right, let's look at this one. Write a C++ program that computes the sum of integers 0 through n, where n is an integer entered by the user. So n would look, like this. But you know what? You don't need to write this stuff. I don't need that. I'm saying, n is an integer entered by the user. So this is what it would look like in code, but it's not really needed. So I'm going to take that out, but that's essentially what that is. The n is a given. N is a given. Now that we have the n, let's compute the sum of 0 through n. So that's a loop. We can use what's called an accumulator. We have an integer. This is how you solve this problem. You've got an index. You've got an I, which is an index that's going to range from 0 to n. And then you have an accumulator. This is the thing that's going to sum up this. For each value of I, you're going to add it into this accumulator. We'll call it sum. We're going to initialize it to 0. Accumulator. Did I get the spelling right? All right. So say it's an accumulator of values. Zero through n. So we're going to need to repeat this operation. We're going to take what's in sum, add what's in I, and then write it back into sum. I'm getting sloppy here. So we take what's in sum, add it to I. That's the right-hand side of that expression. And the result we write back into sum. And we're going to do this, and then let's see if I'll just write it out here. And then I'm going to increment I, and we're going to do this while I is less than or equal to n. So I starts at 0, and then we increment I here, and we test it while I is less than or equal to n. That means I, because we're incrementing by 1 here, I is starting at 0, it'll go to 1, that'll go to 2, 3, 4. If n is 100, I is going to hit 100. I'm sorry, if n is 100, I will hit 100, add 100 into our sum, and then it's going to hit 101, but we don't add 101 into the sum because 101 would make the loop condition false, so we're done. You know, sum is the answer, right? Or maybe I don't want to write it like that. You would do something like this, or you want to print it out. Once again, that's an optional. Not asking for it. I'm looking for this piece of code here that ends there and goes up to there. I can see that sum holds the value. You would output it, or perhaps you would return it. Now, later we're going to look at functions. This is where we return the value from a function. The function's purpose is to calculate the sum. We return the function. We return the value that way. We'll look at that soon. So this is kind of like the first step toward understanding linear algorithms. So a linear algorithm is where you have a sequence of values. And you want to process that sequence. So we have a sequence of values 0 through n, 0, 1, 2, like that through n. And we want to take each of those values and add them together, accumulate their values into a single variable. And that's the sum of those numbers. So you need an accumulator, and you have to have a variable that ranges through the sequence. I starts at 0, goes to 1, goes to 2. All those values are added into sum here. Then you need a loop condition to exit. Let me show you how to do this with a for loop. So we need also, this is the alternative solution here. It's important to remember you need to allocate a memory to accumulate the values, and it needs to be initialized to 0. Unlike other languages, in C++, there is no default initialization when variables are declared. You can't just say int sum. You have to say int sum. Give me a sum, but make its initial state 0. So either one of these will solve the problem. And once again, this is not really necessary. Any questions on this? This is the beginning of doing lots of different kinds of algorithms that process data. And this is where computers suddenly become useful, because now maybe n is a billion. And maybe we're not going to add them up, but maybe it's a billion users on Facebook, and I want to check each and every account and see how many ads they clicked on this month. I've got to do a billion checks. So it's an algorithm. That's where computers start becoming useful for large numbers of things, large numbers of data. All right, let's take a look at number 8 here. Oh, actually, I was supposed to modify these. This one I think you can do. This one here, This one here, I want to talk about this. We haven't really discussed conditionals. And I want to talk about this here. Two things I'll talk about. The yeah, I guess we can do that. Oh, this should be C out, sorry. All right, what do these expressions print? This is, this symbol here, it's called modulo, or mod. 3 mod 1, that's how you read that, 3 mod 1. This is the complement to integer division. Integer division does a division and throws away the remainder. Modulo does a division and throws away the quotient and gives you the remainder. So if you take, you know what? This is not right. This is not what I wanted to do. Sorry. I want to divide by 3. Okay. So this does 1 divided by 3, and I get a quotient and a remainder, and we toss away the quotient, we just take the remainder. So the remainder is 1. In the second one, we take 2, we divide by 3, and we get a quotient of 0 and a remainder of 2. We toss out the quotient, so we just get 2. 2 is the remainder. Here we take 3 divided by 3. We get 1 as the quotient and 0 as the remainder. We toss out the 1, which is the quotient, and then we get 0. That's the remainder. So we're just taking the remainder. 4 divided by 3, well, that gives us 1 and a third, right? So the quotient of 1 and the remainder of 1. When we toss out the quotient, just take the remainder, so we get 1. That's called modulo, the modulo operator, and that's used a lot, actually. So you need to reason about programs that have that use the modulo operator. And let me talk about rand here. So rand is a function. So this is what I want to do. Let's I want to display a random value between 0 and 2. That's what I want to do. See out, how can I generate a random value between 0 and 2? Well, rand gives me a random integer. So that's some value between 0 and the largest positive integer. How can we use that to generate a 0, a 1, or a 2 randomly? Using modulo. See, if you divide whatever the integer you got, if you divide by 3 and throw away the quotient, you're going to get, for a remainder, either 0, 1, or 2. So that's it right there. that's how to generate random value between 0 and 2 inclusive. How about display a random value between 7 and say 7 and 10, or 7 and 12. Well, I'm going to take my code from here. See, 7 and 12, so the random value is needs to either be a 7, an 8, a 9, like that. That's what. So we'll use rand, divide by something. Oops. Take rand and divide by something, and it will add it to 7. So rand divided by anything sometimes gives us 0. So that'll give us the 7 part. And but we don't want to add more than 5, right? So 5 would be the maximum. If rand divided by something gives us a maximum of 5, that'll hit 12 for us, and that's what we need. So this would become 6, because rand divided by 6 it's never going to give us 6 as a remainder, because 6 divides into 6. It gives us 5 as the maximum remainder. So this is the expression you use to generate a random value in some range that doesn't start at 0. All right, one more topic. What was that I was going to do? Oh yeah, if statements. I suppose we're building a video game, and we have a character in the game it tells us something different each time. I mean, not completely different, but there's some random. We want random behavior in the character. So we sometimes walk up to the character and he says, "You're bad." Sometimes it says, "You're good." All right, so we want that to be kind of like a random outcome. So let's generate a random number between 0 and 1. Now x will be either 0 or 1. We don't know exactly. But if x happens to be 0, then the character says, "You're good." But if x is not 0, then we're going to say, "You're bad." There it is. That's our AI for a game that we're building. Generate, we have 2 possible outcomes, and we want them to appear randomly in the game. So we need a random value that's going to take on it's going to take on 2 different states. We need to test for each of those 2 states, and based on what the state is, we'll do one or other outcome. What happens if, let's do it like this. The game designer says, that's boring, and we want a third outcome. I don't know about you. How do we do this? This is how that would look. Now we want x to take on 3 states. 0, 1, or 2. Oh, that means we've got to increment this value here, the divisor. So this expression here, x will take on values 0, 1, or 2. It gives us 3 different states. If it turns out that x is 0, you're good. If x is 1, well, you're bad. And otherwise, it's going to be 2. Then I don't know about you. Now the character's a little more interesting now. So these are called conditionals. This is an if statement. And the else clause here, it's optional. You can have an if statement without an else. But an if takes a condition just like a while loop. Should look at this. When I look at this, it looks like it looks very similar to a while loop. This is a condition. It's a Boolean condition. When it evaluates to true or false. If it evaluates to true, we're going to execute the body of the if statement. It's just like the while loop. It's a loop condition. Evaluates to true, we're going to execute the body of the while loop. The difference between the while loop and the if statement is the if statement runs once, we don't repeat it. So it doesn't loop. It just does, it gives us branching. We can do this or do something else based on some condition that we calculate. Any questions about the Boolean values, Boolean conditions? You need to read up on that and practice that. Yeah?
Why does it require 2 equal signs instead of 1?
Oh, good. We have to use 2 equal signs because this equal sign, that is an excellent question, thank you. I would have forgotten that. This operator is called assignment. This is not assignment. If we use a single equal sign, that will become an assignment. We won't get the correct result. This is a double equal sign, it's called comparison. This is the comparison operator. Thank you very much for that. It's a source of bugs. This happens all the time, and the program will malfunction here. If you do it like this in C++, this statement will never run, because this expression will always evaluate to false. And x will become 0 always. And this will not run. This is the only outcome that will ever happen with this bug. Because this assignment, after the 0 is assigned to x, the expression itself, in a sense, vanishes and is replaced by the result of the assignment, which is 0. And 0 is interpreted as false. And that means this will never run. And x will end up being assigned 0. So it will overwrite the result of this calculation. So this will always be false as well because x will always be 0. That means we'll always branch into this else condition. So that is a very common bug. And in fact, it is a problem, a weakness of the C++ language. Sorry about that. Other languages will catch that mistake and give you a compilation error there. But in C++ or the C language or the JavaScript language is another example where this bug happens a lot. But in some languages, like C#, for instance, the language is, in this case, easier to program with because it won't compile if you get the wrongness, if you use the assignment operator in an if condition. That's it for today, and I'll see those in lab who are coming to lab.